Hi, everyone. We're going to get started. Thanks for coming to our talk. I know this is like almost last talk of the day, so thanks for showing up. Today, we're going to be talking about scaling server-driven UI with the power of Kotlin. I'm Laura Kelly. I'm a software engineer at Airbnb.
And I'm Nathanael Silverman. I also work at Airbnb as a software engineer. We're both on what we call the design language team at Airbnb. And so we build the UI infrastructure that other engineers use to build Airbnb's Android, iOS, and web apps. And so the central goal of our team is to enable fast, high-quality product development. And so for the next 30 minutes or so, we're going to tell you about some of the projects that helped us do just that. So we'll start by taking a quick look at Airbnb's products and some of the bottlenecks in their development. Then we'll briefly look at Airbnb's design system and how it provided a partial solution. We'll see how this design system set the stage for server-driven UI. We'll talk about what server-driven UI is, its benefits, and some of its major challenges. At this point, we'll be ready to introduce Lona, the server-driven UI solution that Laura and I have been working on for over a year now. And last but not least, we'll talk about how Kotlin enabled all of it.
So before we get into the technical details, I'm going to talk a little bit about how we got here and why we started thinking about scaling UI development practices in the first place. A few years ago, Airbnb was quite different. Airbnb started as an accommodations business. We offered one product, homes. At this time, all our engineers worked on supporting that one product. But in 2016, we did something that radically changed the scope of our business. We introduced experiences, which are activities led by a local expert. This changed Airbnb from just being an accommodations app to being a full-fledged travel app. And since then, we've added more features to the app. For example, we introduced Airbnb Plus, which is a curated set of thoughtfully designed homes with standard amenities. And we also added Lux, a luxury tier of homes. We've been adding many products, and we needed to scale our infrastructure across products and use cases to match this. Additionally, our product engineers were building all of these products across 3 different platforms because we have an Android app, an iOS app, and a web application. So whenever we built a similar screen, we were also having to build that screen across 3 different places. And finally, as Airbnb was growing as a product, our engineering team was also growing rapidly. We had many engineers joining who needed to learn how to use our infrastructure, but our product teams were growing faster than our infrastructure teams. Our infrastructure team remained pretty lean. So at this point, we needed to enable rapid, complex development in our applications. We needed to scale our development practices to fit all of these different constraints. The first thing that we did to support this was build something called the design language system. And now Nathanael will talk a bit about what the design language system is.
So Airbnb's design language system, or DLS for short, was created about 4 years ago. And it's basically just a collection of guidelines for designing screens inside the Airbnb applications, regardless of which platform we're designing for. And like most design systems, we have guidelines around the use of the Airbnb logo, or things like colors, or typefaces. But one of its more innovative concepts is row components. And it's a level of abstraction that is unusually high for a design system. And I'll illustrate this with an example screen. So here are parts of the Airbnb listing detail screen. This is a real listing. And some design systems at their very highest level would provide guidelines around all of these elements. So the system would help you design these individual elements, and maybe would have some rules about how you position them relative to one another, and you would compose them to create a new screen like this. Repeat with every screen you need to create. And so, of course, Airbnb system also has to work out all of these details, right? But it goes just a little bit beyond by defining rows. And so constructing a screen with DLS ends up looking more like this. So here we're just stacking row components in a single vertical dimension. And many of these components already exist, and we reuse them across the application multiple times. Now, do note that this concept mainly applies to mobile. Desktop layouts get more complicated, as you might imagine. But this is how Airbnb's mobile applications are built, and they contain hundreds, if not thousands, of screens that follow this pattern. And so by providing reusable row components and other resources, DLS helps with speed. But there's still room for improvement. One of the major inefficiencies is that we still have to build each screen separately for each platform we support, Android, iOS, and web. And unlike web, which can deploy its changes instantly, Android and iOS changes can take days due to the App Store approval processes. Now, quality and consistency have also improved, of course, since we're reusing the same components across the application. However, again, since each platform is a separate project, they're not always on par, not always on sync. And so there have been several initiatives at the company to try to further improve this situation. And the vision is always the following. Can we build screens once for all platforms? And I think there have been many talks today about how to do this in various ways using Kotlin. And can we deploy the changes instantly to clients? And so many of the solutions that emerge within Airbnb were variations of a cross-platform, server-driven system. And we generally refer to those as server-driven UI. And Laura's now going to talk a little bit more about this.
Okay, so now I'll define what we mean by server-driven UI. But first, in order to define it, let's talk about what is not a server-driven system. So here, this is kind of a typical REST API response. You've got an object with a name, you've got an object with a location, and that will have things like an address, country, and so forth. You've got a website object and some photos, which might contain some URLs or UUIDs. So in this typical API response, your client is receiving objects like location, and then it has to take those objects and glean pieces of data into them and then somehow interpret them into a UI component. So hard-coded in your client somewhere, in each client that's consuming this response, it has to know, okay, I'm going to take that address and I'm going to put it in my map UI component. So this is not server-driven. In contrast, a server-driven API response at a high level might look something like this. We would have a carousel object, which maps to a carousel UI component, a title row, an action row, and a map row. Server-driven UI is when the API tells the client what components to render and with what content. Effectively, the server is sending up instructions to the client about what to display. The client has no idea what data is in these instructions. It doesn't know that this is a location object. It just knows when I see a map row, I'm going to render a map row. And so now if we decide to change something in our UI, we can just change that API response and change the action row and title row order. And very similarly, if we change our mind and want to just have a totally different UI component here, we would change our API response to have a different component, like the button row. And now every client that's consuming this API response is going to change instantly to reflect that. This is pretty huge on our native clients, Android and iOS, because as Nathanael said, normally we have to go through an approval process that can take a while. So this is fantastic for our native clients. As long as the client supports the type of row that we're making in that API change, there's no review process, we just change the API. Now, I'm showing an example here of server-driven UI in which the API is on a component level. Let me explain what I mean by that. So you can think of server-driven UI as a continuum. And on one side, you have like different implementations. You have an implementation where the client is going to be implementing it. So an example of this would be that REST API that we were looking at. The client is going to almost solely decide how this API is implemented on the client side. And then on the other end of the spectrum, the server might control every aspect of your UI. So a good example of this is HTML. In an HTML layout, every pixel might be controlled by the server because it controls what in the layout gets sent to the client. Somewhere in the middle, we have component-based server-driven UI. The client still controls some of the fine-grained details, like, for example, the exact placement of a button within a component would be left up to the client. But what is shown, like which components are shown and in what order, is determined solely by the server. Because Airbnb already has a powerful component-based design library, we chose to use components as the basis of our server-driven UI. In our system, our design language system components are the building blocks. The client implements them natively, so the details of how they're actually implemented are left up to the native client. But the server tells the client which components to display, with what order, and with what content. Now I'll show you a specific implementation of a JSON API response that we use at Airbnb in a server-driven system. We built a server-driven system internally called Lona for general-purpose server-driven UI. Let's take a look at what the JSON format looks like for this system. Okay, so here we're specifying a really basic component. The first thing to note is that there's a type here, and the type is my component. This is telling the client which component it needs to render. Then we've got some content here, so we're going to send up a title and a subtitle to place in that component. And let's say that we want this component to be interactive on the client. We can specify that too with something called an action. In this action, we're going to designate an onPress action that happens. And in this onPress object, we have a couple different things. We have the case, which is also sort of like a type. In this case, we're going to specify a deep link, but you can imagine there might be many options for this. So in our system, we could have dismiss, logout, or an async request. And then because we chose a deep link, we also need to send up a URL as some data to accompany this so that the app knows where to route when we tap on this row. So this is a very basic specification of how we specify a component in our Lona system internally. Now, once you have an API format like this for your server-driven system, there are still a number of challenges that a good server-driven UI system should address. The first one is versioning. Okay, here's a common scenario. You launch your new server-driven system, and you have some initial components. Then time passes, you want to launch a new feature, so you're going to add a couple more components and some new properties. You push those changes up to your clients, and you release a new version of your Android and iOS app. Now you turn on the API. So what's wrong with this picture? Well, a lot of users don't update, just because users don't always have their updates turned on automatically, so you may have some version of your app out that's really old for a long time. And for native apps, this means that there's usually going to be many different kinds of your app out in the wild at any given time. But only a few of them are going to be able to understand the newest version of your API. In other words, your API is going to move fast, but your clients are going to update slowly. A good server-driven system needs some way of keeping track of this. It needs to accommodate an API that evolves faster than its users update. A related issue is keeping clients in sync. So in a server-driven system, it's challenging to make sure all of these disparate platforms are rendering the same thing and supporting all aspects of your API as it changes. Another thing that we found to be an issue is scaling. So remember that we have those 3 different tiers of homes. Even within our design language system, these 3 tiers of homes all have pretty different components that they display. It's almost like each product has a design system within a design system. When we first started using server-driven UI, the way that teams dealt with this is they would build a different server-driven platform for each of these different use cases. And in fact, we ended up with over 10 different specific types of server-driven systems. It was a lot of duplicate engineering work to rebuild a system every time you needed something for a new use case. And you might think an easy way to get around this would just be build one system that supports all components in your component library. but this also has its downsides. So in the world of web and Android, features can be delivered dynamically. The app downloads the feature code as the user tries to access it. Of course, this is the default way of accessing a feature in web, and it's now a feature of Android as well. So the user is waiting while the feature downloads. So it's critical that the downloaded code is minimal. We don't want to ship the entire component library that could possibly be supported in the entire app for this reason, because we don't want users to be waiting for a gigantic download. So this is a challenge in the server-driven paradigm because you also want to be able to support all these different use cases, but without this performance hit of downloading every single component when you're just trying to display some of them. And finally, documentation is a really big challenge of this server-driven paradigm. A widely used server-driven system is going to be constantly changing, and even a simple system will have many different permutations of supported platforms, supported app versions, and supported features. So it's really crucial that engineers can be able to predict that when they launch a feature, it will actually work, because it will have dire consequences if they get that wrong. So it's important to keep documentation up to date as the API changes. The Lona JSON format alone that I showed you earlier doesn't solve any of these challenges. That's just part of the picture. But thinking about these common difficulties that we are seeing across other server-driven systems at Airbnb, we came up with a solution for Lona that addresses all of these. And now Nathanael will talk a bit about how we address these challenges with something that we call the Lona Spec.
Thank you, Laura. All right, so we knew right from the get-go that Lona would interact with at least 4 systems, right? Android, iOS, web, and the backend. And each of these systems would have to share a common understanding of what's available in terms of components and other things. And so the backend needs to know which components it can send down to Lona clients, and Android, iOS, and web, as the clients, they need to know which components they're expected to be able to render. And it's easy to imagine how disastrous it could be if these systems are not in agreement for whatever reason. For example, say the backend believes it can use a given component, but the Android client doesn't know about it. Suddenly, a part of the screen is missing, or worse, the application might be crashing. So we knew we needed a source of truth, and it wasn't just a simple list of component names. As we've seen in the Lona JSON format, each component includes a list of typed properties. We also need to keep track of all the versions of the spec which are available. Components in Lona support events and actions, as well as logging and styles. And we actually won't go into the details of all those features, but suffice it to say that the Lona spec needs to keep track of a lot of different things. And so as these requirements became apparent, we turned to Kotlin for 3 reasons. Number 1, I was tasked with writing the prototype of this spec, and I'd been using Kotlin on Android and some smaller projects for a few years already, so I felt comfortable using it for this. Number 2, we knew that other engineers on other teams at Airbnb would need to contribute to this project regularly for their own feature development. And so Kotlin already has a strong presence at Airbnb among the Android team and a growing one among the backend team. Funny story, in fact, about a year after we started using Kotlin on Android, a backend engineer who had transitioned from working on Android wanted to convince his new teammates on the backend team to switch from Java to Kotlin. So what does he do? Well, he sends a poll to all the Android engineers, and he asks the question, would you go back to Java if you could? And so the answer, as you can see, was a resounding no. And so we also have anonymous Kotlin heroes in our offices who post Kotlin lessons in restroom stalls. So they're titled Kotlin on the Potty, and the lesson changes every month. So we were very confident that a significant number of engineers at the company would be able to easily contribute to a Kotlin project. And reason number 3 for picking Kotlin was its DSL features. So it's great if new contributors already know the overall programming language that you're using, but getting up to speed in a new code base can still be very challenging. And DSL, if you haven't yet encountered the term, means domain-specific language. Kotlin has a feature called type-safe builders that's extremely well-suited to creating DSLs. In fact, I'm betting most of you here have heard of them before, probably use them as well. And so we thought that a DSL would help us keep our code clear, succinct, and self-documenting. We also knew that it would be easy to extend it as we added more features. So this is what we came up with. So we start with a component function to add a new component to our spec. And of course, it can be repeated to add multiple components. The first parameter is the component type. It's its unique identifier, if you will. And the second type is a type-safe builder. Now, the type-safe builder creates a component block, and inside we can add a description of our component for documentation purposes, just explaining when and how to use it. And we can also, of course, define content properties. So here we're adding a title property to our header component, and all we need to do is specify its name and type. Content properties also have type-safe builders, and so we can provide a property description, also for documentation purposes, as well as one or more example values. And we've made adding at least one example value per component property mandatory, and there's a runtime check which enforces this. And that's because we use these values to do property-based testing, and I'll talk a little bit about that in just a few minutes. And content properties are mandatory by default, but we can also define optional ones using a separate function. So here, for example, we're adding a subtitle property. Because it's optional, we have to specify its nullability as well as a default value. As a quick note, since we're using Kotlin here, it's really easy to package content property definitions as functions that can be reused on multiple components. For example, we have many components with an optional subtitle property, and so we can define the property like this, and we can use it inside of multiple component blocks like this. So this DSL is looking pretty good. We can add components, we can add properties. Now, as Laura mentioned earlier, versioning is a huge challenge of server-driven UI, and we haven't tackled it yet. Now, our design system, DLS, has been around for a while, and so we know that pretty much anything can change over time. New components can be added, they can be removed, and they can change. So that's all fine and dandy from the point of view of the design system, but working in a server-driven UI context imposes a couple of major constraints here. Number one, you have to assume, as Laura mentioned, that there are clients out in the world running all the different versions of our system because users don't necessarily upgrade. So this means that our spec needs to keep a record of what was included in each version. Number two, we can't ask internal users of Lona to update their pages every time a new version of the spec comes out. So that means that new Lona client implementations need to be backward compatible. They must be able to render pages which conform to an older version than what they support. And so to fulfill these requirements, we built in versioning into our DSL. And we enforced a rule that changes to the Lona spec, had to be additive. New components can be added, but they can't be removed. And similarly, new component properties can be added at a later date, but they must be optional. So let's look at some code again. Back to our DSL, I've got the first version of my header component, and I've already published it, so any changes would require creating a new version now. We invoke the min version function to create a version 2 block. Now we can add any number of new properties which will be scoped to this new version. So for example, here we're adding a sort of arbitrary property which controls whether or not to show a divider at the bottom of the component. We could add different one, multiple ones, and so forth. And a similar min version function can be used to scope entire components as well. So here I can add a component to version 2 of the spec. And of course, these can be combined to specify all the versioning we need, whether it's components or properties. So now we can fully define our server-driven UI specification in Kotlin. And since it's all code already, it's particularly easy to leverage this source of truth and automate as many things as possible. As we've talked about already, we knew that keeping things in sync between multiple platforms was also a challenge. And so one of the first things we did was use this Kotlin specification to generate an equivalent JSON specification so that any Lona client could consume it and test itself against it. This is what this JSON spec looks like at a glance. We generate one file per version of the spec. Excuse me. It has a list of components. Each component has a type and a list of content properties. So this is basically, so far, the exact same information that's contained in the Kotlin spec. In addition, the JSON spec also includes component instance examples. So this is the JSON format that we use to build actual screens to render on clients, following the format that Laura was talking about earlier. And so we talked about property testing when defining content property examples. And this is where it comes in. So examples generated here test all the possible example values. So this particular example here uses the short title value. The next one uses the long one. And so contents or components with more content properties or more example values can have many more entries like these. And so using the JSON spec, our current clients are able to validate their implementation. They can check that they support all the available components and the properties for any given version of the spec. And they can also check that they are indeed backward compatible. We also generated JSON schemas so that JSON Lona pages can be validated in any context. JSON schema is a standard for describing a JSON data format. We didn't come up with it. And so there are already many tools and libraries and many languages that already exist and make it possible to validate JSON against a given schema. Here's a random online JSON schema validator. On the left, we plopped in the JSON schema that is generated by the Lona spec. And on the right, we can start typing JSON following our formats, and then this website tells us if it's valid or not. So this makes it possible for both humans and backend services to validate Lona pages. Next, we generated documentation so that humans could easily read and share our specification. Here you can see a particular component. All of the properties are listed. We even have JSON examples in here for what we might use for this component or how we might use it. And all of this is just generated automatically and regenerated anytime the spec is changed. And so, of course, it would be possible to just read the Kotlin code and understand what's available in the system, but generating this separate documentation makes it more readable and makes it also easily shareable with people who might not be able or need to contribute to the Kotlin project. And so at this point, validating a Lona page is much easier than creating one. And so we created a page builder specifically for Java or Kotlin services. And right now it looks something like this. It's its own DSL. Here, instead of calling a component function to add components to our spec, we're calling component instance to create instances of components which have to already exist in the spec. Everything else is specified in a type unsafe manner. And so the type of the component is a string, so are the property names. All the validation happens at runtime, which it's good that we have validation, but it's not ideal, of course. And so right now we're working on generating a type-safe page builder. So each component will get its own function, and the properties will be passed as parameters, and it'll also manage all the versions for us. And so with this, the backend can safely and easily build Lona pages that are guaranteed to work on all the different clients. Now at this point, we've addressed three of the four major challenges. So versioning, keeping clients in sync, and documentation. And the last one is scaling. So for a while, the system worked great, but as more and more teams started to use it, the spec kept growing. It was becoming difficult to manage versions, and performance was also becoming a concern due to the number of components. And that's when we added modularization features. So instead of a single spec definition, we made it possible to define spec modules, which are effectively separate specifications. It enables teams to create their own modules. They can exclude the components they don't need. They can release their own spec versions at their own pace. As we've seen, our design system relies on reusing components. And so we made component spec definitions reusable as well. Those are defined at the top level of the spec project, like this. And they can be used and reused instead of spec modules, like this. And so that's how Kotlin helped us solve the biggest challenges of server-driven UI. We Kotlined it, or codified it. None of these sound right.
So using this system at Airbnb, we've had teams build out a lot of features with Lona. For example, this is one example. It's a screen that shows up if you log into the app before a trip, and it will suggest things for you to do on your trip. Another feature that was really successful that we think really shows just how easy this system is to use is we had a partner team that was doing a hackathon, and they came to us and they said, okay, we have one day, we want to build a feature to drive employee adoption of the beta app. So in just one day, they built out this screen that will pop up in the Airbnb app when an employee accesses it that says, hey, do you want to download the beta app and dog food our app? So they built this out in one day and launched it to a bunch of employees, and it really shows that when you get these things right, you can build features really quickly. So in conclusion, using a Kotlin DSL to power our server-driven UI framework increased our speed of iteration across Android, iOS, and web. It gave us the ability to build once and deploy instantly. It gave us better consistency across platform, eliminating differences between the spec and the clients. And it gave us better quality with our app. Now, because we have this DSL powering everything, we can be confident with our testing framework that when we launch a new feature, it will be supported on the clients we expect it to be supported on. Thanks for listening to our talk. We won't be taking live questions, but if you want to come down here and chat with us, we'll be sticking around. Thank you.